Can we design a 3D printable heat exchanger without spending $30,000 on specialized software? Let's find out. With Halloween just around the corner, there's nothing scarier than burying your temperature gauge in the red. So today we're going to take a look at designing and 3D printing a heat exchanger, two of them actually, with gyroid geometry. I initially chose this stacked plate water to oil heat exchanger to keep the oil temperatures in check on the turbo rotary that's going in my BMW i8. This style cooler is often used by OEMs because of its compact size and high efficiency, and also generally eliminating the need for a thermostat controlled bypass. On a cold startup, the oil temps will trail that of the coolant, so the coolant will help to put heat into the oil and bring it up to operating temperature faster. Likewise, once the car is up to temperature and you begin to drive it in anger and the oil temp starts to rise, the coolant will then try to bring that back down as the cooler reaches an equilibrium. This particular cooler was one of the largest OEM units I could find, has a nice flat mounting flange, -8 oil fittings, and 5/8 barb on the coolant side. This all resulting in a nice, easy to integrate package. There was, however, a problem. That is that this is a Chrysler Dodge part that suffers from an extreme rate of failure. When these fail, it's typically an internal brazed joint that splits and then mixes oil and coolant to create a forbidden milkshake. When you have a car that has a cooling system that runs through the entire length of the vehicle, then that makes a giant sludgy mess. My second miscalculation was that I assumed wrongly that due to the high failure rate that there would be multiple options in the aftermarket for a robust upgrade. I failed to take into account that the demographic of ownership for these vehicles deals with this repair in one of two ways. Number one is that they will simply delete the cooler, because who needs that anyway? The second will buy the cheapest part that the internet has to offer and then replace it time and time again until they delete the cooler. There was, however, one company that made a billet upgrade, and from the photos it appears that there are two separate cavities to split the oil and coolant, and then I assume that there are some sort of fins or channels internal to help with thermal transfer. However, at $600, I decided that I could probably do something better using 3D printing and gyroid geometry. Autodesk Fusion has a volumetric lattice tool that will generate a gyroid structure from any solid body. This is normally part of their paid product design extension, but they offer a free 30-day trial that we're going to use here. This is the point at which I got a case of tunnel vision and then continued down a path that may not result in the most optimum result. To create the first cooler in Fusion, all I did was to make a body that was roughly in a similar dimension to the OEM style cooler. Out of that, I created two separate halves, shelled out each half to create a separate body, which will then become our gyroid lattice. And then after spending either a whole bunch of money or enabling your free trial, you just click on modify and then volumetric lattice, and then you can select your gyroid cell shape and the body that you want to create. Now you can't click on both bodies at once, you have to do them individually. And then you can play around with some of the parameters in there. You can change the size of the gyroid, the density, and then we can also change the direction and orientation of the cell structure itself. At this point, you really can't do anything with this body. So if we go and export this as an STL mesh body, and then if we go and open it in an external 3D model viewer, you'll see that it's nothing more than the original solid body that we created. So if we jump back into Fusion, then we right click on it, convert volumetric model to mesh. To minimize our poly count and reduce our pain level, let's just keep the resolution at low. And then after Fusion churns for a few seconds, we now have an actual detailed volumetric lattice that is a mesh body. Unfortunately, now that you have this mesh body, it kind of is what it is. If you try to do a shell modification or anything like that, it's just going to fail because it's going to be far too complex for Fusion to handle. Because we can only convert one body at a time, we'll do the other one. And just for demonstration purposes, we'll change some of the parameters a bit. And then now if we export the whole body as a mesh, now if we open that up in our external 3D viewer, we can see that all the features we created would be 3D printable and turn into a tangible part. This is where we ended up on the final iteration of this cooler. You see the separate mesh bodies still exist as meshes. We didn't convert them into solids, nor would you want to. We just want to make sure that there's enough interface with the outer bodies so that it exports as a complete model. Now that the design is wrapped up, as with most of our aluminum prints, we're going to use the services of CraftCloud, and pricing on this one comes in just under 500 bucks. added access windows to this part so the manufacturer would be able to remove the aluminum powder more easily from the assembly. They did a pretty good job here, and there was minimal material left inside. This will ultimately go pre-oil filter, so I'm not really concerned about a stray piece of debris. And if you've never cut apart an oil filter after a fresh build startup, then you'd probably be pretty horrified at what's inside. As I alluded to earlier, this isn't the proper usage of gyroids in a heat exchanger, nor is a gyroid structure that Fusion generates the proper application for a heat exchanger either. A true TPMS gyroid, meaning triply periodic minimal surface, is going to create a structure with two independent flow paths, and that means that the oil and coolant is going to have a repeating series of channels that are going to flow adjacent next to each other. Now, the term minimal surface might sound counterintuitive, but this structure actually results in the maximum surface area for a given volume. When done correctly, this results in a heat exchanger that is one of the most efficient designs in existence. This structure can only be realized through the use of additive manufacturing, which is the reason that we don't see it at scale in large OEM applications, because it is cost prohibitive. In the professional design world, to achieve these complex designs, there's a software called NTOP. It is, however, $31,000. That's not in the budget for this project, and their marketing folks didn't answer my emails in regards to a video collaboration, so we turn to the next best thing, and that is YouTube. I found a tutorial from 7 years ago on how to create a gyroid cell in Blender. Now, I generally avoid using Blender at all costs because I don't find that software at all intuitive, but it's a step-by-step tutorial, so how bad could it be? As it turns out, I had to download the matching 7-year-old version of Blender so that I could create the base features and then bring the software into the latest release to finish the design. So after opening the completed file in the latest version of Blender, we now have a single cell TPMS gyroid, and I added a few modifiers here so that it is somewhat parametric and that we can generate an array of such gyroids that we can then import into Fusion. The dimensions here are accurate. I don't know what's going on with the scaling. I'm not really all that up to speed with Blender as a general whole, but let's try out this array situation. By changing the count of gyroid cells, you can make a cube or rectangle in any sort of dimension that you want. You can see right here about 170 by 270 by 100 millimeters. And before we go and bring this into Fusion, you can see at the edges that they're not really great for building any sort of flat features off of. So we're going to have to go through and make a Boolean cut with a cube to get us to our final shape. So you can see that after we make that cut, we then have some flat faces that we can build some block offs, because we're going to have to block off the alternating channels to ensure that our oil does not mix with our coolant. But this is now ready to export into Fusion and then integrate it into our design. I will make this Blender file available on Cults 3D for about $5. So if you want to use this file for your own gyroid generation, then think of it as buying me a beer for my troubles. We can then bring our gyroid mesh into Fusion. We can treat this somewhat like a 3D scan and then do a mesh section sketch to project the geometry from each of the sides on here. And then what we're going to do with those is create alternating block off plates for each of the channels. So by doing this, you create independent sealed off channels, and then we can integrate this into a fully functioning cooler. So because on the mesh we did not block off any of the tops or bottoms, we're just going to interface that with the exterior of our body shell. You can see that it just coincides with the top here. That's going to be flush, and you're not going to see any of that stuff when you export the final mesh. But when you export it as a single body, that will then include all of your gyroid stuff for the 3D print. To access internally here and get all the metal shavings out when we tap this thing, I have some weld-in panels on the bottom that are going to be laser cut, and then we have some support bars to keep this thing intact. And as usual, we have liberal application of hexagons. Speaking of software, you may have seen something called Shaper on other channels, and it is a very, very easy to use aerodynamic CFD analysis tool, which also now offers internal flow analysis, which we'll look at here to compare the two designs. With the software, we can visualize the surface friction internal to the model as well as turbulence. With the cooler, we actually want turbulent flow so that it maximizes the contacts between the fluid and the cooling surface. If you have nice smooth laminar flow, only the boundary layer of the fluid is going to have contact and conduct heat. Now that we've got all that in place, we're going to place another order with CraftCloud for about the same amount of money and have version 2. Before we go and finish this thing off, it's worth touching on a couple things about the part as it arrives. First of all, anything that you get that's this kind of chunky is going to be susceptible to maybe some warping or deformation. And if we take a look at the holes, for example, right here, that's pretty much perfect. But on this side, you can see that it's just a little bit misshapen, and that doesn't really matter because we're just going to send this port tool down there. That'll clean up the hole and then cut the O-ring groove. But just something to always keep in mind that if you're expecting a perfect finish, that's not always going to be the case. A smaller part is going to be much more true to dimension, but the fact that this is based on powder that's all welded together, just like a traditional welded part, if you have a big chunk of metal and then a thin portion, you might get some deformation or warpage between the two areas. So it's just something to keep in mind. As you saw from the CAD, this design was a little bit different. We kept the channels separated and the access points from the bottom. This is going to allow us to clean up the metal that we're going to weld to much better than this iteration. For the patch panels, rather than having printed parts, because this is flat, I used our friends over at SendCutSend for some filler pieces. You can see that there's a little bit of warping where this pinches a little bit closer. So what we're going to do is when we clean up the edges here, we'll probably taper that a little bit. Same thing on this, and then it'll be almost a press fit into place, and that's going to make for a nice clean tight weld joint. Internally, we can see some support bars. These are essentially going to keep the outer walls from exploding because they're pretty thin. The wider passages are going to be for the coolant. That is going to be because the operating pressure is only going to be 16 to 20 psi. Likewise, on this end, we're going to have our oil passages. We have much less surface area to create any deflection or problems. If I remember correctly from the FEA, the burst pressure on the oil side was 400 psi, and the coolant side, I believe, had a burst pressure of around 150 psi. If we get that much pressure in our cooling system, then the oil cooler is probably the least of our concerns. All right, I think that's enough on this. Other than that, I'm really happy with how this came out. It looks great, solid, really nice details on the text and all the hexagons. So let's go and finish this one up. Before we go any further, it's probably a good opportunity to talk about when you're designing something for 3D printing in metal that you're going to weld, particularly aluminum. You're going to want to spend some time and make sure that the backside and edges of the weld, everything that might draw impurities into that weld, is going to be accessible to clean. As you can see on the first cooler, I wasn't able to clean it as well as I liked. Reasonably okay weld. I'm not super thrilled with it. Part of it also was dialing in some of the settings on the new Everlast Typhoon 330s. And then you compare that to this one, and you can obviously see it welded much, much cleaner. Both of these are from the same vendor, by the way. Same material, same quality, I would say. But here we were able to clean it much better and have a significantly better result. This was also welded at a slightly higher AC frequency, which seemed to help keep things localized and was much easier to control the overall shape and width of the weld puddle. This is our highly scientific test rig. We've got 2 diaphragm pumps that are going to circulate our hot water and our soon-to-be cold water through our heat exchangers. Then we've got 2 temperature sensors in the outlet hoses from our heat exchanger, and those are going to feed an STM32 microcontroller that are going to log the temperatures every second to an SD card. As a side note, I will provide a link to this development board in the description, because if you want to get into any sort of embedded programming, things like that, this is a really great board. It's got an LCD touchscreen, 3 onboard CAN transceivers, LEDs, push buttons, Ethernet, basically anything that you would ever want to learn and develop on a single board. I think it's less than $100, but I will give a link to that. This all ties into a power strip, so with a press of a button, we can then fire the pumps, start logging simultaneously, and then let this thing run for either 3 to 5 minutes. I haven't figured that out yet. And then we'll be able to use that as a comparison. And then I also have a thermal camera pointed at this so we can see how the heat transfers, which should be kind of interesting. Now, I also have to mention this is an imperfect test setup. It is not going to directly translate to the performance on the car. All we're trying to do is establish a baseline between the 3 coolers to basically compare their thermal transfer performance. On the vehicle, we're going to have differing flow rates on both the coolant system and the oil side, and the oil is going to have a different thermal transfer property than the water, but again, it's just going to give us a comparison of how well each of these coolers is going to transfer heat from one side to the other. To heat our water, we've got a simple immersion heater, and I think I'm gonna just run this until the water boils. And then on the cold side, we're going to take water that is fresh out of our hose spigot outside, and that's gonna be fairly consistent as a baseline. And what we're gonna do is record the values as they change over time, and then the delta between those two is going to be basically what we're gonna compare. And what we want to see is that that delta gets smaller faster with the more efficient cooler, and with any luck, the factory replacement Dodge cooler will be the worst, followed by my Fusion gyroid, and then finally, I really hope that the best performance is with the true TPMS dual channel gyroid of the final iteration, but we will find out shortly. All right, we're just starting to boil. I think that's good enough. We are going to send it. Thermal imaging here is thanks to a TC003 from TOPDON, which is a tablet-style thermal camera. It's super easy to use, and we'll be making regular appearances anytime we're doing temperature-related analysis. Let's take a look at the data for the 3 different styles. We've got our hot side temperature, our cold side temperature, and the delta between those two. We have a pretty consistent baseline starting temp of roughly 200 degrees Fahrenheit on the hot side and about 65 degrees on the cold side. Each of the rows represents 1 second of elapsed time, bringing us to 180 seconds for our 3-minute runtime. First, we'll take a look at our OEM style cooler, which is going to serve as our baseline reference and brought us to a final temperature of 135.5 degrees Fahrenheit. The first printed cooler we'll look at is of the Fusion style Gyroid, and this only brought us to a final temperature of 172.4 degrees. So we shed roughly 30 degrees over 3 minutes. This makes total sense in hindsight, and if I wasn't so impatient to get something off to Craft Cloud for production, I would have likely never had this design manufactured. Finally, we'll take a look at the gyroids that we generated in Blender, and we have a much better result. This brought us to a final ending temperature of 127.6 degrees, which was the lowest out of all 3 coolers tested. If we directly compare the hot side temps between the OEM style and the gyroid style, we can see that we dropped temperature significantly faster and then maintain that drop throughout the rest of the test. Then if we compare the temperature delta between the hot and cold sides, we can see that the gyroid heat exchanger resulted in a much faster transfer of temperature before falling in line to a rate that was more comparable to the OEM cooler. So did I create a better cooler? Well, maybe. It did result in the lowest temperature out of the 3 units tested, and I now also have a homogeneous 1 millimeter thick wall between the oil and coolant that I have a lot more confidence that I'm not going to create chocolate milk down the road. The test scenario was imperfect, but the data does seem to indicate that we're trending in the right direction. But living that corporate life, more fiction is written in Excel than Word, so we're going to have to do some actual in-application A/B testing. The way that this is going to be mounted in the car, it's going to be fairly accessible and easy to swap that out when the time comes. I'm sure I've managed to anger some actual thermodynamics experts out there, so feel free to unleash your rage in the comments. And if you made it this far, thanks for watching, and we'll see you next time.